Find somewhere comfortable, somewhere soft and still. You don't need to follow any of this closely. You don't need to remember a single word. Just let the sounds arrive and let them drift past you like something seen from a slow-moving train. We're in no hurry tonight. If today was hard, you can set it down now. Whatever you carried through it, the small frustrations, the unfinished things, the low hum of worry that follows you from room to room, none of it needs to come any further with you. This is a different kind of place. Quieter, older in a way. Tonight we're going to travel somewhere vast. Not forward, but backward. A long way back. Further than any history you've ever been taught. Further than the first cities, the first fires, the first living things. We're going back to a moment before any of that was possible. Before anything that could be called a thing at all. It is a journey to the very beginning of matter itself. To the first particles, the first forces, the first patient assembly of everything that has ever existed, including you. You don't need to concentrate. You don't need to understand every detail. Just let it wash over you like warmth, like something ancient and gentle settling across your chest. The universe has been here for 13.8 billion years. It is in no rush either. Close your eyes, if they aren't already. The story begins a very long time ago. Before the first second, before the first fraction of the first second, before any unit of time small enough to have a name that would mean anything to you. There was something. Not silence, exactly, not darkness, not emptiness. Those words describe an absence, and what existed in that first impossible instant was not an absence, but a presence so extreme, so concentrated, so searing and total that none of the words we use for ordinary things come anywhere close to touching it. The universe, in its very first moments, was a single point, a point of pure energy, not matter. Matter did not yet exist, not space, not in any sense you could picture. Not time, not in any direction you could follow, just energy, compressed to a density that has no comparison in anything you have ever experienced or imagined, existing at a temperature so far beyond what any thermometer could record that the number itself becomes almost meaningless. Physicists write it as 10 to the power of 32 degrees. That is a 1 followed by 32 zeros, and even then the number is only an approximation of something that language was never built to hold. And yet, in that point, everything was latent. Every atom that has ever formed, every star that has ever burned, every ocean, every mountain, every living cell, every person you have ever loved, all of it was there. Folded into something smaller than anything we can directly measure, waiting without knowing, because waiting requires time, and time had only just begun. The universe expanded, not into anything. There was no space outside it to expand into. Space itself unfolded, and as it unfolded, it cooled. This is the central rhythm of the story we are telling tonight, expansion and cooling. Those two words repeated across 13 billion years are responsible for everything. In those first extraordinary fractions of a second, the universe was so hot that what we now think of as the 4 fundamental forces of nature, the 4 distinct ways in which the physical world exerts influence, were not 4 things at all. They were one. A single unified force operating in conditions so extreme that the distinctions between its parts were dissolved, the way different instruments in an orchestra are dissolved into a single wall of sound when played at full volume in a very small room. The 4 forces, as we know them now, are these: gravity, which draws mass toward mass and holds planets in their paths around stars; electromagnetism, which governs the behavior of light and electric charge, which holds atoms together into molecules, and molecules into the materials of the world; the strong nuclear force, which binds the particles at the center of every atom together with an almost incomprehensible grip; and the weak nuclear force, which governs certain kinds of radioactive decay, allowing one type of particle to transform into another under the right conditions. These four forces feel very different from one another. Gravity is familiar, constant, invisible, and extraordinarily weak at the scale of individual particles. The strong nuclear force is powerful almost beyond reckoning, but it operates only across distances smaller than a single atomic nucleus. The weak force is strange and subtle, responsible for processes that happen deep inside stars and in the hearts of atoms. They seem, today, to be four entirely separate things. But in those first moments, they were not. The image that has stayed with physicists and science writers for decades, and it is a beautiful one, is of a single note separating into a chord, one pure tone, as the universe cooled, gradually splitting. The unified force, as the temperature dropped through certain critical thresholds, began to peel apart. Gravity separated first, becoming its own distinct thing, perhaps within the first tiny fraction of a second. Then what physicists call the electro-weak force, the unified form of electromagnetism, and the weak nuclear force, separated from the strong force. And then, a little later still, as the cooling continued, electromagnetism and the weak force divided from each other too. Each separation happened as the universe passed through a kind of phase transition, the same kind of transition that turns water into ice when the temperature drops through zero, or turns liquid metal into solid when it cools in a mold. The physics changes. New structures become possible. Old ones become locked in. By about 1/10,000,000th of a second after the beginning, still an almost impossibly brief sliver of time, all four forces had become distinct. The chord had fully sounded. And the universe, still unimaginably hot, still containing no matter in any recognizable form, was ready for the next stage of its long, patient becoming. There is something worth sitting with for a moment, before we move on. The idea that everything, your hands resting on the bed, the walls of the room around you, the air moving gently in and out of your lungs, was encoded in that first instant, not built yet. Not even close to being built yet, but latent, the way a symphony is latent in the silence before the conductor raises the baton. The universe did not know what it was going to become, but it was already carrying the rules that would make becoming possible. That is where we begin. For the first millionth of a second or so after the beginning, the universe existed in a state that has no everyday equivalent. No solid, no liquid, no gas. Something older and stranger than any of those. It was a plasma, but not the kind you might picture if you've seen a plasma lamp, those glass spheres with colored lightning coiling inside them. This was something far more fundamental. The universe, in this era, was filled with what physicists call a quark-gluon plasma. A hot, formless broth of the most basic known ingredients of matter, moving freely, colliding constantly, not yet able to organize themselves into anything more structured. To understand what this means, it helps to go one level deeper than the atoms you might be familiar with. You may know that atoms have a nucleus at their center, a tiny, dense core containing protons and neutrons, with electrons moving around the outside. And you may know that protons and neutrons are themselves made of smaller things. Those smaller things are quarks. As far as we currently know, quarks are fundamental. They have no internal structure we can detect. They are among the smallest known building blocks of matter. Quarks come in different varieties, which physicists have given the slightly whimsical name of flavors. There are 6 flavors in total, though only 2 of them matter for the protons and neutrons we're most familiar with. These 2 are called up and down. An up quark carries a fractional electric charge, 2/3 of the basic unit of charge. A down quark carries -1/3. The specific combinations of up and down quarks determine what particle they form, and we'll come to those combinations shortly. But in the quark-gluon plasma, quarks were not yet combined into anything. They moved freely through the hot broth, and moving with them, equally free, were the particles that carry the strong nuclear force, particles called gluons. Gluons are the messenger particles of the strong force, in the same way that photons are the messenger particles of electromagnetism. When two electrons repel each other across empty space, they do it by exchanging photons. When quarks interact through the strong force, they do it by exchanging gluons. The name is apt. Gluons act like glue, binding quarks together. But in the quark gluon plasma, the temperature was so extreme that this binding couldn't hold. The quarks had so much energy that they could move independently, slipping past one another like they were swimming in a very hot, very dense sea. There is something almost meditative about picturing this state, a vast, formless ocean of particles, no structure yet, no hierarchy, no protons, no neutrons, no nuclei, no atoms, no molecules, nothing you could point to and name. Just an ancient, patient broth, everywhere at once, expanding slowly as the universe grew, cooling degree by degree. And here is where the story becomes genuinely wonderful, because we don't only know about this state from theory, we have actually made it. At the relativistic heavy ion collider, a particle accelerator at Brookhaven National Laboratory on Long Island in New York, physicists have spent years smashing gold atoms together at very nearly the speed of light. The collisions are so energetic that for a brief instant, the protons and neutrons in those gold nuclei melt. The quarks and gluons come free of one another. A tiny droplet of quark-gluon plasma forms, lasting for perhaps 10 to the power of minus 23 seconds, a duration so short it makes a millionth of a second seem geological in comparison, before cooling and recombining. Similar experiments have been conducted at CERN, the European Particle Physics Laboratory near Geneva, using their Large Hadron Collider. There, beams of lead nuclei are brought to collisions at even higher energies, creating droplets of this ancient state and allowing scientists to study its properties. What they found was a surprise. Before these experiments, most physicists expected the quark-gluon plasma to behave like a gas, a collection of free particles bouncing off one another with little interaction. Instead, it turned out to behave more like a liquid. Not just any liquid, but something extraordinary, a near-perfect fluid, one with almost no internal friction, no resistance to its own flow. Technically, physicists describe this as having an exceptionally low ratio of viscosity to entropy, viscosity being the measure of a fluid's resistance to flowing, entropy being a measure of its disorder. The quark-gluon plasma, it turns out, flows more freely than anything else ever measured, more freely than water, more freely than liquid helium. It is, in the words of scientists who work with it, the most perfect liquid ever observed. This was genuinely unexpected, and it tells us something deep about the nature of the strong nuclear force, that even when quarks are free to roam, they are still intensely, intimately interacting with one another through the constant exchange of gluons. The early universe, then, was not a gas of free particles loosely drifting. It was a dense, flowing, nearly frictionless liquid of quarks and gluons, hot beyond any modern comparison, expanding outward in all directions, cooling with every passing moment. And in that cooling, something was waiting to happen. The quarks were moving more slowly with each passing instant. The energy holding them apart was diminishing. The conditions that had kept them free were becoming gradually untenable. The broth was preparing to set. About 1/10,000,000th of a second after the beginning, still a fraction of time too small to hold in your mind as anything real, the universe crossed the threshold. The temperature had fallen far enough. The energy of the quark-gluon plasma had dropped to a point where something new became possible. The strong nuclear force which had been present all along, exchanging gluons between quarks in that dense flowing sea, finally had enough of an advantage to do what it does best. It bound them together. This moment is called quark confinement, and it is one of the most profound transitions in the entire history of the universe. From this point forward, quarks would never again move freely. In the universe as it exists today, and as it has existed for almost all of its 13.8 billion year history, a single quark alone has never been observed. They exist only in groups, locked together by the strong force into composite particles called hadrons. The reason for this confinement is one of the stranger and more beautiful facts in all of physics. Most forces weaken with distance. Gravity between two objects becomes weaker the further apart they are. The electromagnetic force between two charges falls off in the same way. Double the distance, and the force drops to a quarter of what it was. This behavior is so familiar that it seems almost like a law of common sense. The strong force does not behave this way. When two quarks are very close together, the strong force between them is actually relatively weak. They can move around one another with some freedom. But as they try to move apart, the force does not diminish. It stays roughly constant, and then it grows. It is as though the quarks are connected by a rubber band, not one that snaps when stretched far enough, but one that never snaps at all and simply pulls harder and harder the more you try to separate them. The energy stored in this stretching bond is so enormous that if you tried to pull two quarks apart with enough force to separate them completely, something else would happen first. The energy you'd put into the bond would spontaneously generate a new pair of quarks, one at each end of the stretched connection. You would not end up with a free quark. You would end up with two new composite particles, each containing their own paired quarks. Nature, it seems, simply does not permit quarks to be alone. This is confinement, and it means that from about 1/10,000,000th of a second onward, the universe was a place where quarks existed only in combination, bound into hadrons, the family of particles built from quarks. The most important hadrons, the ones that would go on to build every atom in the universe, are the proton and the neutron. A proton is built from 3 quarks, 2 up quarks and 1 down quark. Add up their fractional charges, 2/3 plus 2/3 minus 1/3, and you get exactly 1 unit of positive charge. That is the charge of a proton, the charge that defines the nucleus of a hydrogen atom, the charge that electrons are drawn toward. A neutron is also built from 3 quarks, but with a different arrangement, 1 up quark and 2 down quarks, 2/3 minus 1/3 minus 1/3. The charges cancel. The neutron carries no electric charge at all. 2 quarks difference. 1 up quark swapped for 1 down quark. That is the only distinction between a proton and a neutron. And yet that small difference, that single quark's worth of distinction, carries consequences that ripple through all of chemistry and all of biology and all of human existence. Because the number of protons in an atom's nucleus is what determines which element that atom is. Hydrogen has 1 proton, helium has 2, carbon has 6, oxygen has 8, carbon has 6, oxygen has 8. The entire periodic table, the entire diversity of matter, rests on how many protons are stacked at the center of each atom. And those protons are built from up and down quarks. The distinction between every element in the universe traces back to those 2 quark flavors and to the moment 1/10,000,000th of a second after the beginning, when they stopped being free to drift and began to commit. As the first protons and neutrons formed, their antiparticles formed alongside them. This is a feature of how matter comes into being at high energies. Particles are produced in pairs, a particle and its antimatter twin. The antiproton is identical to the proton in every measurable respect except that its charge is negative. The antineutron is its own kind of mirror image, composed of antiquarks. And when a particle meets its antiparticle, they annihilate. Both disappear in a flash of pure energy, photons radiating outward. In those first fractions of a second after confinement, the universe was full of both matter and antimatter, protons and antiprotons, neutrons and antineutrons, colliding and annihilating constantly, releasing energy, generating new pairs, annihilating again. a furious, cycling exchange between matter and light. Whether any matter would survive this exchange was not yet decided. That depended on something delicate, something almost imperceptibly small. A tiny ancient imbalance that would turn out to be the difference between a universe full of things and a universe containing nothing at all. Imagine a vast bonfire, not a bonfire of wood and leaves, but a bonfire of existence itself. Matter and antimatter, meeting in equal quantities, consuming each other completely, leaving behind nothing but light. That is what should have happened. By every symmetrical account of the laws of physics, the early universe should have annihilated itself. Every proton should have found an antiproton. Every neutron should have found its mirror. The great cancellation should have been total. The universe should be empty. The fact that it is not, the fact that you are lying in a bed made of matter, in a room made of matter, on a planet made of matter, inside a galaxy made of hundreds of billions of stars made of matter, is one of the deepest and most quietly astonishing facts in all of science. Something, in those first fractions of a second, was not quite symmetrical. The balance was off by the tiniest of margins. For every billion antiprotons, there were 1,000,000,001 protons. For every billion antineutrons, there were 1,000,000,001 neutrons. One extra particle of matter for every billion pairs. The billion pairs annihilated, and that one leftover particle, the residue, the remainder, the ash of the great bonfire, survived. Every atom in your body is descended from one of those survivors. Every star you have ever seen in the night sky is built from them. All the matter in the observable universe, hundreds of billions of galaxies, each containing hundreds of billions of stars, is the remnant of that 1 in a billion excess. The question of why this asymmetry existed at all is one of the most important unsolved problems in physics. We know it happened. The universe is here to prove it. What we do have is a framework for thinking about it. In 1967, a Soviet physicist named Andrei Sakharov, who was also, separately, one of the most prominent human rights advocates of the 20th century, a man of remarkable moral courage, published a short but extraordinarily influential paper. In it, he identified 3 conditions that any explanation of the matter-antimatter asymmetry must satisfy. These conditions have been known as the Sakharov conditions ever since. The first condition is this: the universe must have treated matter and antimatter differently at some point. The laws of physics, as we understand them, are very nearly symmetrical between matter and antimatter, but not perfectly. There are certain reactions, certain decays of particles called kaons and B-mesons, studied in detail at particle accelerators, in which matter and antimatter behave slightly differently. This violation of the symmetry between them is called CP violation, where CP stands for the combined operations of swapping a particle for its antiparticle and mirroring it in space. The standard model of particle physics, our best current description of fundamental particles and forces, does predict some CP violation, but not nearly enough to account for the full asymmetry we observe in the universe today. The second condition is that certain reactions must have been able to proceed in one direction, but not easily reverse. In physics, this is related to the arrow of time, the observation that some processes in nature are irreversible. A cup falling and shattering does not spontaneously reassemble. The universe, in its early moments, needed some reactions that preferentially produced matter over antimatter, without the reverse process cancelling them out. The third condition is that the early universe must have passed through a period of being out of thermal equilibrium, a state in which different parts of the system are at different temperatures or energies, so that the usual statistical averaging that would otherwise erase any asymmetry is disrupted. A universe in perfect equilibrium would continually re-establish balance. Only a universe in flux, out of its own steady state, could lock in an asymmetry before it was erased. All 3 of these conditions are believed to have been met in the early universe. The details of how and in what combination remain a subject of active research and genuine uncertainty. There are many proposed mechanisms, some involving a period of the universe's very earliest expansion, some involving exotic new particles that have not yet been directly detected, some involving subtle effects of the weak nuclear force at extreme temperatures. None of them is yet confirmed as the full answer. What is confirmed is the result. The asymmetry existed, matter survived, and the universe, having spent its first fraction of a second in a fury of creation and annihilation, emerged from that fire carrying its residue, a thin, precious layer of matter distributed through an expanding space of almost unimaginable size. The protons and neutrons that survived the great annihilation were now the dominant form of matter in the universe. The light released by the annihilation, an enormous quantity of photons, filled space in every direction, and the universe, still extraordinarily hot, still far too energetic for anything as complex as an atom to hold itself together, continued to expand and cool. The protons and neutrons drifted in that hot sea of light, occasionally colliding, occasionally sticking together briefly, then being torn apart again by the ambient heat before anything stable could form. But the temperature was falling. The energy was diminishing. And somewhere ahead, about 1 second into the universe's existence, the conditions were approaching that would allow something new. The first nuclei were almost ready to be born. By the time the universe was about 1 second old, it had already lived through more dramatic transformations than the rest of its history would contain. The forces had separated, the quarks had bound. The great matter-antimatter annihilation had run its course. The surviving protons and neutrons were drifting in a hot, dense bath of photons and neutrinos. Neutrinos being ghostly, nearly massless particles that interact barely at all with ordinary matter, passing through almost everything as though it weren't there. At this point, the temperature of the universe was still roughly 10 billion degrees, too hot for atomic nuclei to survive. Any two particles that stuck together would immediately be blasted apart by the surrounding radiation. But the cooling was continuous, and the clock was ticking toward a brief and remarkable window. Between about 1 second and roughly 20 minutes after the beginning, the universe passed through a phase that cosmologists call Big Bang nucleosynthesis, or primordial nucleosynthesis. It was the first time in the universe's history that atomic nuclei could form and survive. And in that window, the basic chemical composition of the entire universe was decided. The story of this window begins with a ratio. Before nuclear synthesis began in earnest, the balance between neutrons and protons was being continuously adjusted by the weak nuclear force. The weak force allows a proton to transform into a neutron and a neutron to transform into a proton through reactions involving electrons and neutrinos. At very high temperatures, these transformations happen rapidly in both directions, keeping the numbers of protons and neutrons roughly equal. But as the universe cooled and the neutrinos became less energetic, these weak force reactions slowed and eventually froze out, stopped happening at any significant rate. At the moment they froze, at about 1 second after the beginning, the ratio of neutrons to protons was locked in at roughly 1 neutron for every 6 protons. This ratio is not arbitrary. It was set by the balance between the weak force reactions and the cooling rate of the universe, which in turn depends on how many types of particles existed to carry energy. The fact that this ratio turned out to be approximately 1 to 6 and not 1 to 2 or 1 to 20 is one of the most consequential accidents, if accident is the right word, in cosmic history. There is a complication. Free neutrons are unstable. A neutron not bound inside a nucleus will decay. It will spontaneously transform into a proton, an electron, and an antineutrino, with a half-life of about 10 minutes. So as the universe cooled and the conditions for nuclear fusion approached, the clock was running. Any neutrons that didn't get incorporated into a nucleus within roughly the first 10 to 15 minutes of the universe's existence would decay away. leaving only protons. Fortunately, the universe moved quickly enough. As the temperature dropped through about 1 billion degrees, comparable to the interior of a massive star, protons and neutrons began to fuse together and hold. The first step was the formation of deuterium. A deuterium nucleus is simply a proton and a neutron bound together, what you might think of as heavy hydrogen, since a normal hydrogen nucleus is just a lone proton. For most of the first few minutes, deuterium was being formed and immediately destroyed by high-energy photons. Physicists call this the deuterium bottleneck, until the radiation field cooled enough to stop disintegrating deuterium as fast as it formed. The path to heavier nuclei was blocked. Once the temperature dropped enough for deuterium to survive, things moved quickly. Deuterium nuclei fused with protons and neutrons to form helium-3, 2 protons and 1 neutron, and with each other to form helium-4, the most stable nucleus of all, 2 protons and 2 neutrons, bound together with an exceptionally tight grip. Helium-4 is so stable that once formed, it is very difficult to destroy. It became the primary destination for almost all the neutrons in the early universe. The arithmetic is elegant. With roughly 1 neutron for every 7 protons at the time, nucleosynthesis became effective. The ratio had shifted slightly from 1 to 6 as some neutrons decayed during the deuterium bottleneck. Almost all the neutrons ended up paired inside helium-4 nuclei. 2 neutrons per helium nucleus paired with 2 protons. That used up 2 of the 7 protons. The remaining 5 protons, and there were no neutrons left for them, became hydrogen nuclei. Lone protons, the simplest possible nucleus. The result, by mass, was roughly 3/4 hydrogen and 1/4 helium. With trace amounts left over, a little deuterium that didn't complete its fusion, a little helium-3, and a small quantity of lithium-7, whose nucleus contains 3 protons and 4 neutrons. That is the recipe. 3/4 hydrogen, 1/4 helium, with traces of deuterium and lithium. It is the recipe for the chemical composition of the universe as a whole, set in the first 20 minutes of existence and not significantly altered until the first stars began to burn, billions of years later. What is astonishing, genuinely and quietly astonishing, is that this prediction was worked out on paper in the 1940s by a physicist named George Gamow and his collaborators, including a young graduate student named Ralph Alpha. Gamow was a brilliant and somewhat theatrical scientist, known for his sense of humor as much as his science. He famously added the name of physicist Hans Bethe to the paper listing Alpha as the first author, simply so the author list would read Alpha, Bethe, Gamow, echoing the first 3 letters of the Greek alphabet. The paper, submitted in 1948, was the first detailed theoretical account of how the light elements formed in the early universe. The prediction it contained, that the universe should be approximately 3/4 hydrogen and 1/4 helium by mass, has been confirmed by every observation made since. Astronomers measure the composition of ancient stars, of gas clouds in distant galaxies, of the oldest and most chemically pristine regions of the universe, and they find the same ratio, 3:1 hydrogen to helium by mass. The theory and the universe agree with a precision that is still remarkable to sit with. The universe was now carrying its first chemistry. Not complex chemistry, not molecules, not life, not anything close to those things. Just nuclei, just protons and helium nuclei, and a scattering of deuterium drifting in a hot, bright sea of photons and electrons. Simple, patient, vast. But the electrons were still free, and as long as they were free, the universe could not become transparent. The next great transformation was still nearly 400,000 years away. After the first 20 minutes, the universe entered a long quiet. Not a quiet of emptiness. The universe was still extraordinarily hot, still densely filled with particles and radiation, still a place of constant, furious activity at the microscopic level. But in terms of dramatic transitions, in terms of new structures forming or fundamental changes occurring, the universe settled into a kind of holding pattern. It expanded. It cooled. For nearly 400,000 years, the state it existed in during this time was a plasma, but a different kind of plasma from the quark-gluon broth of the very first instance. By now, protons and helium nuclei were present, stable, drifting through space. And electrons were present too, freed from any attachment, moving through the hot gas at enormous speeds. But the temperature was still far too high for those electrons to be captured by the nuclei. Any time an electron slowed enough to approach a proton and begin to be drawn in by its electric charge, a high-energy photon would come along and knock it free again. The electrons could not form. And because the electrons were free, moving independently through the plasma, present in vast numbers in every direction, light could not travel freely either. This is the crucial point of this era, the thing that makes it so distinct from the universe we inhabit now. Photons, particles of light, interact strongly with free electrons. When a photon encounters a free electron, it scatters, it bounces off in a new direction, its path redirected. In the early universe, with free electrons everywhere, a photon could not travel more than a short distance before being scattered again. And again. And again. The universe was opaque, not dark. It was filled with light, intensely bright, but foggy in the deepest possible sense. Light existed everywhere and could illuminate nothing because it could never travel in a straight line long enough to carry an image of anything to anything else. Imagine standing in the thickest fog you have ever seen. You can tell it is bright around you. Light is diffusing in from every direction, but you cannot see more than a few meters in any direction. The early universe was like that, except the fog was made of electrons and the distances involved were cosmological, and the fog extended in every direction for the entire observable universe. This is the state the universe maintained for roughly 380,000 years, not static. The plasma was slowly thinning as the universe expanded, slowly cooling as the expansion continued. But no dramatic transitions, no new structures, just the patient, gradual descent toward a critical temperature. That temperature was approximately 3,000 degrees, still hot, far hotter than the surface of the sun, which sits at around 5,500 degrees, though the comparison is slightly misleading since conditions were so different. At 3,000 degrees, something changed. The electrons, which had been moving too fast to be captured, had slowed enough. The photons, which had been too energetic to allow stable atoms to form, had cooled enough. And in a transition that swept across the entire universe over a period of perhaps a few tens of thousands of years, fast by cosmic standards, though long by any human measure, for the first time in the universe's history, there were complete neutral atoms. And the moment this happened, the moment the free electrons disappeared into their new atomic homes, the fog cleared. The photons that had been endlessly scattering, bouncing from electron to electron, suddenly found that there were almost no free electrons left to scatter from. They streamed forward. For the first time, light could travel freely across space. The universe became transparent. This event has a name, recombination, which is slightly misleading since the electrons were not recombining with nuclei they had previously left. They were combining for the very first time. The name is a historical accident, but it has stuck, and it marks one of the most significant moments in the universe's history. The light that was released at recombination, the photons that finally streamed free after nearly 400,000 years of being trapped, did not disappear. It has been traveling ever since. As the universe expanded over the following 13 billion years, that light was stretched. Its wavelength grew longer, its energy diminished. Light that was once in the infrared, warm, gentle radiation, has been stretched all the way into the microwave region of the spectrum. It is still arriving, Right now, from every direction in the sky, ancient photons, relics of the moment the universe first became transparent, are washing over the Earth. They are the oldest light in the observable universe. They carry, imprinted in their faint patterns, a snapshot of what the universe looked like at the age of 380,000 years. We call this the cosmic microwave background. And it was discovered not by a telescope pointed at the sky, not by a theorist working through the mathematics of the early universe, but by two engineers in New Jersey who were trying to track down an annoying hiss. In 1964, Arno Penzias and Robert Wilson were working at Bell Laboratories, attempting to use a large horn-shaped antenna, originally built to receive signals bounced off early communication satellites, for radio astronomy. They kept encountering a persistent, uniform background noise coming from every direction, regardless of where they pointed the antenna. They checked their equipment, the antenna. They removed a pair of pigeons that had been nesting in the antenna and cleaned out what they diplomatically described in their paper as white dielectric material, pigeon droppings. The hiss remained. Eventually, through a series of conversations with theorists at Princeton who had independently been working to predict exactly this kind of signal, Penzias and Wilson realized what they were hearing. They were hearing the echo of creation, the faint, stretched remnant of the light released when the universe first became transparent, arriving at their antenna after a journey of nearly 14 billion years. Penzias and Wilson were awarded the Nobel Prize in Physics in 1978. The pigeons were relocated. The universe, by the time of recombination, had built its first atoms and released its oldest light. It had taken nearly 400,000 years to reach this point, an almost incomprehensible stretch of time after the breathless pace of the first 20 minutes. And in the ancient light now streaming freely across space, information was encoded. Delicate, faint variations in temperature and intensity that would eventually tell us almost everything we know about where we came from. The cosmic microwave background is not perfectly uniform. If it were, it would be beautiful, but not particularly informative. A smooth, featureless glow from all directions, telling us only that the early universe was hot and dense. What makes it extraordinary? What has turned it into perhaps the most scientifically productive observation in the history of cosmology is that it is not quite smooth. Across the sky, there are tiny variations in temperature, regions that are fractionally warmer, regions that are fractionally cooler. The differences are small, about 1 part in 100,000, but they are real and they are not random. They are a fingerprint. To understand what these variations mean, it helps to think about what the early plasma was actually doing during those 380,000 years before recombination. The plasma was not perfectly uniform. There were slight density differences, regions where matter was fractionally more concentrated and regions where it was fractionally more rarefied. These density differences arose, according to our best understanding, from a period very early in the universe's history called cosmic inflation, a hypothesized phase of extraordinarily rapid expansion in the universe's first tiny fraction of a second, during which quantum-scale fluctuations, the kind of random, irreducible variations that are built into nature at the smallest scales, were stretched to macroscopic and eventually cosmic sizes. Inflation is still a hypothesis, not a confirmed fact, but its predictions match what we observe in the CMB with remarkable accuracy. These density variations set up something extraordinary in the early plasma, acoustic oscillations. This is the technical name for pressure waves, essentially sound waves, though in a medium nothing like air. That propagated through the hot plasma, where matter was denser, the pressure was higher, and the plasma pushed outward. Where it was more rarefied, it fell inward under gravity. The plasma rang, in a sense. It vibrated with pressure waves at specific frequencies determined by the conditions of the early universe, the density of matter, the density of radiation, the rate of expansion. When recombination happened and the plasma froze into neutral atoms, these pressure waves were caught mid-oscillation. The pattern was locked in. The temperature variations in the cosmic microwave background are the fossilized record of those ancient sound waves, the last note played by the early universe before it fell silent. Reading that record has required extraordinary instruments and extraordinary patience. The first confirmation that the CMB temperature variations existed at all came from a satellite called COBE, the Cosmic Background Explorer, launched by NASA in 1989. For 2 years, COB scanned the entire sky, building up a map of the microwave background with unprecedented precision. In 1992, the team announced their results. The temperature fluctuations were there, at exactly the level that theory predicted. The scientific community received the announcement with what is, for physicists, an unusual degree of open excitement. Stephen Hawking described it at the time as the greatest scientific discovery of the century, possibly of all time, a characteristically large claim, the one that reflected how significant the detection was. The principal scientists behind COBE, John Mather and George Smoot, were awarded the Nobel Prize in Physics in 2006. But COBE's maps were relatively coarse. They could show that the variations existed, but not their detailed structure. For that, a new generation of instruments was needed. The Wilkinson Microwave Anisotropy Probe, WMAP, was launched in 2001 and spent 9 years mapping the CMB with dramatically improved resolution. Its maps revealed the detailed pattern of temperature fluctuations across the full sky, and from those patterns, cosmologists were able to extract an extraordinary range of information. The age of the universe, 13.8 billion years, was measured from WMAP data with a precision of better than 1%. The rate at which the universe is currently expanding was constrained. The proportions of ordinary matter, dark matter, and dark energy were measured. Dark matter is worth pausing on for a moment because it appears in these maps in a very particular way. Dark matter is matter that does not interact with light. It neither emits nor absorbs photons. It is invisible in the conventional sense. In the early universe, dark matter participated in the gravitational dynamics of the plasma, influencing how the density fluctuations evolved, how the acoustic oscillations rang, at what frequencies the pressure waves peaked. The detailed pattern of temperature fluctuations in the CMB depends sensitively on how much dark matter was present. And from the WMAP data, and from the even more precise data that followed, the answer came back clearly. The universe contains roughly 5 times as much dark matter as ordinary matter. About a quarter of the universe's total mass energy is dark matter. Only 5% is the ordinary matter. Protons, neutrons, electrons, atoms, that makes up everything you can see and touch. The most detailed CMB maps yet produced came from the Planck satellite, a European Space Agency mission that operated from 2009 to 2013. Planck's full-sky maps have a resolution roughly 50 times finer than COBE's, and the data extracted from them have confirmed and sharpened the WMAP results with remarkable precision. The age of the universe, the proportions of matter and energy, the geometry of space, whether the universe is flat or curved like the surface of a sphere, or curved the other way like a saddle. All of these parameters have been measured with a precision that would have seemed fantastical to cosmologists a generation ago. The universe, it turns out, is flat to within the precision of current measurements. It is also, in its large-scale geometry, extraordinarily uniform. The same in all directions, the same at all distances, the same rules applying everywhere. Current experiments are now pushing further still. At the South Pole, an instrument called the South Pole Telescope is mapping the CMB's polarization, the way the ancient light is oriented as it travels, which carries additional information about the conditions at recombination and, potentially, about inflation itself. In the Atacama Desert of northern Chile, At an altitude of 5,000 meters where the thin, dry air allows microwaves to pass through with minimal interference, the Simons Observatory is being constructed to map the CMB polarization across a large fraction of the sky with unprecedented sensitivity. What these experiments are searching for is a specific pattern in the polarization, a swirling, curling signature called B-mode polarization, which would be the imprint of gravitational waves generated during cosmic inflation. Gravitational waves are ripples in the fabric of space itself, produced when anything with mass accelerates. During inflation, the violent, exponential stretching of space would have generated gravitational waves on a cosmic scale, and those waves would have left their mark on the polarization of the CMB. Detecting that mark would be the closest thing we have to direct evidence that inflation happened, a window into the universe's first fraction of a second, encoded in the faint orientation of photons that have been traveling for nearly 14 billion years. The CMB is, in this sense, not just a relic. It is an ongoing source of discovery. Each new instrument that looks at it more carefully finds something new, or confirms something predicted, or raises a question that the previous generation of instruments couldn't even ask. The ancient light is still teaching us. And what it teaches, ultimately, is a story about structure, about how the slight density variations in the early universe, those 1 in 100,000 ripples in the primordial fog, grew over billions of years under the slow, patient pull of gravity into the vast architecture of the cosmos. The galaxies, the galaxy clusters, the enormous filaments of matter stretching across hundreds of millions of light years, with vast empty voids between them. The seeds of all of that were already present in the CMB. The universe, at 380,000 years old, was already carrying the blueprint of everything that would come after. There is a thread that runs from the first fraction of a second to this moment, from quarks to gluons to protons and neutrons, from nuclei to atoms, from the clearing of the primordial fog to the formation of the first stars, from those stars to the planets that formed around them, from those planets to the slow chemistry that eventually assembled something capable of wondering where it came from. That thread runs through you. The hydrogen in your body, in the water that moves through your cells, in the organic molecules that carry your genetic information, in the vast majority of the atoms that make you up by number, was not made in a star. It is older than any star. It was forged in the first 3 minutes of the universe's existence, in the brief, hot window of nucleosynthesis, when the cosmos was 1 billion degrees and protons and neutrons were fusing for the first time. The hydrogen in you has been hydrogen for 13.8 billion years. It has drifted through interstellar space, been gathered into clouds, condensed into a star, been expelled when that star died, gathered again, fallen into the solar nebula that became our solar system, rained down onto the early Earth, entered the ocean, entered a cell, entered you. It is the oldest thing about you. The helium drifting in the atmosphere, the helium in weather balloons, in the voice-changing party trick, in the cooling systems of MRI machines, was also made then. It has been helium since the universe was 20 minutes old. Every helium nucleus you encounter is a relic of primordial nucleosynthesis, unchanged in its essential structure across all the time that has passed. The electrons in your atoms are different in origin, but no less ancient. They were present in the early plasma, scattering photons for nearly 400,000 years, keeping the universe opaque. They were present at recombination, when they finally slowed enough to be captured by nuclei and the universe became transparent. The specific electrons in your body have passed through countless atoms over the history of the Earth. Electrons are exchanged constantly in chemical reactions, flowing through circuits, transferred in the contacts between surfaces. But electrons themselves are neither created nor destroyed in ordinary chemistry. They are, in a real sense, as old as matter. And the light, the photons released at recombination, the ancient light of the cosmic microwave background, is still arriving. Right now, as you lie in the dark, faint microwaves from the moment the universe first became transparent are washing over you from every direction. You are bathed in the oldest light in the observable universe. It carries almost no energy. It has been stretched and cooled across 14 billion years of cosmic expansion, but it is there, the echo of creation, arriving still. There is a way of thinking about all of this that is not cold or overwhelming, but warm, intimate even. The universe did not produce you as an afterthought. You are made of its oldest, most patient work. The quarks that bound themselves into protons in the first millionth of a second, those protons are in you. The asymmetry that allowed matter to survive the great annihilation. That asymmetry is why you exist. The nuclei that formed in the first 20 minutes, the atoms that formed at 380,000 years, the ancient light that streamed free at recombination. All of it is part of a continuous chain that leads, without interruption, to the atoms in your body and the electrons in your brain, and the slow, quiet rhythm of your breathing in the dark. You are not separate from the universe, observing it from the outside. You are a part of it, one of its more elaborate arrangements, one of its more recent experiments, but made of exactly the same ingredients as everything else. The same quarks, the same forces. Physicists sometimes talk about the anthropic perspective, the observation that the conditions of the universe are, in many respects, precisely what they need to be for matter to exist, for stars to form, for chemistry to happen, for life to arise. The strength of the strong nuclear force, which determines whether helium-4 is stable enough to survive. Change any of these by even a small amount, and the universe you get is a very different one. Perhaps one with no stable atoms, no stars, no planets, no anything. The universe we inhabit seems in some sense finely arranged for the existence of things like us. Whether that arrangement is the result of design or of selection from a vast ensemble of possible universes with different properties, or simply of the fact that in any universe capable of producing observers, the observers will inevitably find themselves in a universe capable of producing them. They may never be resolved, but they are worth carrying lightly, the way you might carry a beautiful stone you found on a walk, not as a burden, not as a demand for an answer, but as a reminder that the world is stranger and more generous than it often seems. The universe, after recombination, entered a long, dark age. The atoms were there, distributed through space, cooling slowly. But there were no stars yet. No light sources of any kind. For perhaps 200 million years, a span of time that makes all of human history seem like the blink of an eye, the universe was dark. Hydrogen and helium, drifting in the vast and lightless space, being drawn together very slowly by gravity, gathering into clouds, those clouds collapsing under their own weight, growing denser and hotter at their centers, until, eventually, the first stars ignited. That is another story, the one that follows this one in the long sequence of the universe's becoming. But for now, in the quiet of this moment, it is enough to rest with what has been told. The quarks that bound themselves together in the first millionth of a second, the protons and neutrons that formed and survived, the nuclei that assembled in the first 20 minutes, the long hot darkness of the plasma era. The moment the fog cleared and light streamed free for the first time, the ancient fingerprint of that light still arriving from every direction, still carrying its faint record of the earliest moments. All of it patient, all of it vast, all of it somehow leading here, to this room, to this quiet, to you. The sentences grow shorter now. The story has been told. The universe built its ingredients and rested in the long dark before the stars. You can rest too. The hydrogen in you is 13 billion years old. It has been many things, and it will be many things again. Tonight it is simply here, warm, still. The ancient light is arriving, faint, unhurried. Somewhere behind you, the day has grown very distant. The first atoms are drifting. The universe is patient. Sleep now, if you are ready.